Venetian blinds are a method for constructing subsets of the plane whose projections are large in a very narrow set of directions, and then either small or zero in every other direction. So there's no one theorem or no one set called the Venetian blind theorem or Venetian blind set. However, in this video, we're going to focus on one particular theorem that will be used in the next video when we discuss Falconer sundials. So the statement of the lemma goes as follows. So suppose I have an interval I in the plane. So in this figure, I is this bottom interval going across the slide. So it's an interval parallel to the x-axis. Then for any positive numbers epsilon and rho, we can find a set E that is a union of line segments contained in a rectangle based on I. So imagine that the rectangle is this shape of height rho, such that the following holds. So first of all, if we project in directions between minus pi over 4 and 0, so if we pick a direction in this wedge here, and we project, then the set E contains the interval I. And furthermore, if we project in directions between 0 and pi over 4, so we project in directions in this wedge of directions, then the projection will have small Lebesgue measure. Okay? So the set is constructed in stages. So in this figure, you'll see that I have an interval I, that's this bottom light blue line. And what I do is I specify some number alpha, and I divide my interval I into m many subintervals. And then for each of them, I lift each interval up to the hypotenuse of a triangle that makes angle alpha with the original line I, such that one end of it is still in I, and so that their projections, they project down onto the original m intervals. So thus, as you can see, if I take this set and project in any of the directions between minus pi over 4 and 0, okay, any line going at that angle is going to pass through both these red lines and the set I. And so the projection will contain the set I. Now furthermore, notice that the original interval I, when I projected in a direction parallel to the x-axis, or maybe close to the angle 0, then the projection of my interval was small. However, as I start to move away from angle 0, the projection of my interval I is going to get large. But now that I've replaced the interval with these red intervals, notice now that if I project in this direction or an angle close to that direction, now because I have a bunch of line segments that are close in angle to that direction, those line segments and thus my new set are going to have small projection in that direction as well. So thus, this set is such that if I look at directions close to this one, and if I look at directions close to this one, the projections of my set E will be small. And still, if I look at directions between minus pi over 4 and 0, the projection of E will of these red segments will contain the projection of I. Okay, so now what I do is I keep going. So I take these red line segments, these are my new set, and then I repeat the exact same construction on each one of those sets, dividing each of the red intervals into m many subintervals, and then lifting those intervals up to a hypotenuse of a triangle where one endpoint is still on the interval. So the resulting set I get is now this union of blue lines. So again, the projections close to the x-axis will still be small, and the projections in this direction, because these intervals are so close around the previous red intervals, their projection in this direction is still going to be small. But now we've introduced a new direction, so parallel to these line segments, so that if I project in an angle very close to that direction, or very close in angle to these new line segments, then the projection is small again. And moreover, you can verify that when I take the projection in angles between 0 and pi over 4, so in a direction like this, so any line going in that direction that passes through I will also pass through one of these blue segments. And then the idea is just keep going with this construction, replacing these line segments and so forth until you can guarantee that every angle between 0 and pi over 4 will also have small projection. So let's recap what the previous lemma says. So given an interval I parallel to the x-axis, I can find a set E so that the following holds. If I pick a direction, theta, that is between minus pi over 4 and 0, so as to say this direction points, this direction lies in this blue region, then the projection of E will contain the interval I. Now, if I also pick a direction theta that is inside this red region, so it's in between angles of 0 and pi over 4, then the projection of E is going to be small and less than epsilon. So now what I want to do is take this set and start adjusting it, transforming it, so I can narrow the set of directions for which the projection of E contains the interval I. So I want to make that region as small as I want, and I want to enlarge in the red region as much as I can. Okay, so in other words, I'm trying to find a set E whose projection contains I, the interval I, only in a very narrow set of directions, and then has very small projection almost everywhere else. So the first thing that we're going to do to ease this construction is recall that the set E is a union of line segments that make angles between 0 and pi over 4 with the x-axis. Now what I'm going to do first is we can replace all of those line segments with line segments parallel to the x-axis that still approximate the original set E very well. So the resulting set that I get will have very similar projection properties. So first of all, because it is a union of line segments in a tight space around the original set, that means that it's still going to have very small projections if I project in a direction between 0 and pi over 4. Now, however, if I project in a direction very close to 0, now because my set is now a union of line segments parallel to the x-axis, if I project in the direction theta equals 0, or in a direction close to that, now the projections of these lines will be very small. So I can't guarantee that this blue region, or this region of places where the projection of E contains the interval, I can't guarantee that it's going to also include a small interval of directions just below 0. But it's still going to contain most of the previous directions. So now what I'm going to do is I'm going to pick a affine map that does the following. So first of all, it preserves the x-axis, so it doesn't change anything, and hence this interval I will stay where it is. Secondly, it's going to move this arrow close to the y-axis. And finally, it's going to take this arrow and move it to an arrow right to the left of the y-axis. So what that's going to do is that it's going to expand the blue region so that it contains a neighborhood around the y-axis down here. So let's color that blue. Okay, and then similarly, because the projection in direction theta is the same as projection in direction minus theta, it's also going to contain a narrow interval around the positive part of the y-axis. Okay, and then moreover, when I move this arrow right here, what that's going to do is expand the range of regions where my orthogonal projection is going to be very small. So the resulting set after applying this affine map looks like this. Now notice that because the x-axis was preserved, this set is still mapped to a union of line segments that are parallel to the x-axis. Okay, so the final thing that we'll do is notice that the set right now has the property that if I project in any of these red directions, the projection is small, and if I project in any of these blue directions, the projection contains the projection of the interval I. So now what I'm going to do is take each interval in E and replace it with a copy of the set E. but a reflected copy across the y-axis. So now I'm going to replace it with sets for which the projection diagram here is the opposite, just reflected across the y-axis. And so if I replace each one of these segments with that copy, what that will do is that it's going to force now the projection to be small, not just in these red directions, but also in the red region when reflected over here. Okay, and same thing down here. Right? And then so that means that all that's left over is a very narrow blue strip around the y-axis where my projection will not be small, but where the projection will contain the interval. So in other words, when I reflect the red region over the y-axis, this is the diagram that I get. So now I have a set E that's a union of line segments parallel to the x-axis, where the projection in any one of these directions is now very small, and then in this very narrow set of directions around the y-axis, the projection of E contains the unit interval. So what we've just done is just a proof by picture of the following lemma. So suppose again that I have an interval in the plane parallel to the x-axis, and I have some small number alpha between 0 and pi over 2. Then for any other small numbers, epsilon, rho, and delta, we can find a set E that's a union of line segments parallel to the x-axis, and it's contained in this very narrow rectangle based on I of height rho. So that the following holds. For all angles that are in this narrow alpha neighborhood of the angle pi over 2, my projections of E contain the projections of I. And moreover, outside that interval, or a bit more outside, so for angles theta that are at least alpha plus delta away from pi over 2, the projection is very small. So notice that there is a small delta interval of angles that we can't account for, but that's going to be okay for our application of this lemma because that's a very small interval. The final adjustment we make to this lemma and also to the set E that we construct is that in the proof of the Falconer-Sundial theorem, it'll be more convenient for E not to be a union of line segments, but a union of balls. So we can do this just by covering E by a collection of very small balls that approximates the set E very well, and that will have the same projection properties here. So the reason is that in the Falconer-Sundial theorem, we're going to construct the Falconer-Sundial as a nested sequence of sets, and so it'll be important for us to have a set, for the sets in our sequence, to have some interior. So again, there's no one theorem that is called the Venetian blind theorem. However, this method can be used to construct similar examples with prescribed projection properties. So for example, if you iterate the above construction, you can obtain a set E so that its projection into the real line contains an interval, but all other projections in any other direction are Lebesgue measure 0. One can also change the construction a little bit so that you can actually get a set E of finite and positive one-dimensional measure so that its projection onto any line has Lebesgue measure 0. So in other words, this is a set of positive and finite length, but it has no shadows. It's effectively invisible if you look at it from any direction.